Okay, welcome to lecture here. We're continuing on chapter 12. So we're going to talk about, continue to talk about bonding and all that good stuff. So last time we started talking about bonding and we talked about the two sort of different types of bonding, one being an ionic bond, which is always between a metal and a non-metal. And in that particular case, the metal, because of a lot of those periodic properties that we talked about earlier, is going to be the one that's going to give away its electron. While, excuse me, the non-metal, which has all those properties where it really wants to gain electrons, is going to pretty much pick up those electrons. And it's at that point there where we do get that ionic bond that occurs, and that's the cation for the metal, the anion for the non-metal. And again, it's that opposites attract that holds that together, electrostatic attraction. Again, absolutely no sharing of electrons happening there in our ionic bond. So it's just that positive negative attraction that holds that unit together. And as we've talked about before, the larger that sort of charge, if you will, the larger the positive negative charge, the stronger that attraction is. Kind of the smaller the charge, a little weaker that attraction is. But still, there's absolutely no sharing of electrons that, again, is occurring in an ionic bond. And that's different than a covalent bond where we have really two nonmetals that come together. And two nonmetals that come together basically will end up sharing electrons. And they share electrons because they also have a very similar type of periodic trends. So all of our nonmetals are pretty much in the same location there on the periodic table. Which means they both really want to hang on to their electrons. They don't really want to give away their electrons. So really the best that can happen usually when we get two nonmetals together is that there will be some aspect of sharing. So as we talked about last time, that sharing may be equal sharing of those electrons, and it may be unequal sharing of those electrons. And the way that the electrons are being shared gives us two different types of covalent bonds. One's a nonpolar covalent bond, and in a nonpolar covalent bond, what we essentially have is the electrons being shared equally. And in a polar covalent bond, we have the electrons being shared unequally. Most people just call it a nonpolar bond or a polar bond, but they're both covalent bonds. They're both sharing of electrons that are essentially happening there. And what really helps us determine whether or not those electrons will be shared equally or unequally is what we sort of, I think, finished up on last time, which was looking a little bit more into electronegativity. So electronegativity is the ability really of an atom to bring electrons towards itself. It increases as we go up and to the right on the periodic table, with fluorine being the most electronegative atom we could have. And it decreases as you go left and down on the periodic table. And we also saw that there are some electronegativity values which run from 0 to 4 that we saw in that little chart on Monday. And we could take the difference in electronegativity values to help us determine whether or not we would expect it to be an ionic bond, a polar bond, or a non-polar bond. And again, remember that if you take sort of that difference in electronegativity, and it's anywhere from 0 to like 0.4, that's really considered a non-polar bond. And again, what that essentially will mean is we consider that sort of equal sharing of electrons. Although, as we talked about last time as well, even though you can have something at 0.4 difference, which is technically equal sharing of electrons, is not really perfect equal sharing of electrons like you would at the 0 side. And when you have that 0 difference, as we talked about last time, it is still a nonpolar bond, but sometimes people will classify that as a pure covalent bond, as you have perfect equal sharing of electrons happening. If you got something above 0.4, which is like 0.5 to less than 2, that is usually a polar bond. Again, sharing of electrons here going to be unequal. And if you typically have an electronegativity difference there of above 2, that usually is an ionic bond, which, as we talked about, is no sharing of electrons at all, 100% transfer of electrons from one side to the next. When we do have that unequal sharing of electrons, it does create a partially positive side to the bond and a partially negative side to the bond, which is sometimes referred to as a bond dipole. And we can sometimes relate that with an arrow, where the arrow points to the more negative side of the bond, and the back part of the arrow, which makes kind of like a plus, is the more positive side of the bond. So that, again, sometimes how bond dipoles are sort of represented. Any questions on any of that stuff we talked about last time? Okay, so let's see here. We got this one. We want to arrange these from most to least polar. So this would be a place where we would want to use, say, our electronegativity values. So for example, here, if we look at nitrogen and fluorine, nitrogen has an electronegativity value, I think, of 3. Fluorine is 4. So when we take the difference between those, the difference in electronegativity would be 1. Oxygen has a electronegativity value of 3.5. Fluorine has 4, which means if we take our difference there, we're at 0.5. And lastly here, our carbon has an electronegativity value of 2.5, and fluorine has 4, which means our difference would be 1.5. So the greater the difference in terms of electronegativity, the greater the polar bond, there's the bigger separation of that charge. Electrons are heading further to one side. So we want to go from most polar to least. So this guy right here, CF, would be most polar in that group, it followed by NF, and lastly OF in that particular case would be the correct order, again using the electronegativity values to help us do that. Again, if we look at the second row here, we got 2.5 for carbon, we got 4 there for the CF, so we have our 1.5 difference like we have above. Our nitrogen is 3, and our oxygen is 3.5, so that also is going to be 0.5. So we got 1.5 and 0.5, and silicon is, that's a good question, what is that one? That is 1.8 and 4, so that's 1.8 and 4 there. So that's going to get us, was that, that is 2.2, I think, in that case. So in this particular case, for B, we would have to put it in order. Again, the greatest in order, we would go with the greatest here, which is SIF, followed by CF, and where we got there, NO at the end there. So SIF for that one, CF, and NO, again, based on electronegativity values there. Greater difference in electronegativity, greater polar bond. 2 chlorines here is obviously going to give us a difference of 0 as they both have the same value. Boron is 2. Chlorine is, what we got there, 3, looks like, perhaps. So that's going to be a difference of 1. And sulfur, which is 2.5. And chlorine being 3, which is 0.5. So in this particular case, it would be BCl and SCl and CL. Again, going from most polar to less polar. Question on how to determine that there. Okay. So here, which of the following would be least polar yet still considered a polar bond? So in this particular case, we could just kind of go through some here. We could eliminate this guy. That's a metal, non-metal. So that's going to be ionic. This guy as well, as we just saw, was way over 2. So he's definitely not going to be. O and O, they're both the same, which would have an electronegativity difference of 0, which means it should be non-polar. So that really does leave us B or E in terms of our options here. So if we look at B, which is one of the ones I think we might have done there, we have 2.5 for carbon and 3.5 for oxygen. So that's a difference of 1. Nitrogen is 3 and oxygen 3.5. That's a difference of 0.5. So here we're looking for the least polar, but yet still polar would be E in this case. Question on that one there. And most polar without being ionic. So again, we could kind of eliminate the same deals. This guy is definitely going to be ionic. It's metal, non-metal. We just did, let's see here. We just did these two guys, I think, which was 0.5, I think, and 1. This guy is going to be non-polar, and this guy was over 2, I think. So that was like 2.2, if I'm not mistaken. 2 point. So that's 1.8 and 0, which is our O, which is 2 point, or 1 point. Yeah, a lot of math there. That's thank you, 1.7. I'll get it there. So it would be D in this particular case. I should grab the calculator. All right. Any questions on that particular one there? You would have to look at that table that we saw is a few slides back. It's in here, and it's also in your book. So you would have to look at those values up in that table. It should be, where's that thing? Right there, I think. It was this table that we looked at last time. So that's where you get all those values from. Other questions? And obviously that would be provided for you if you needed it for questions like this. You don't have to memorize it. All right, when considered a bond between two atoms, the greater difference in electronegativity, the more polar the bond is. So as we've been talking about, that should be C, it looks like. Again, we really do use electronegativity to help us decide, as we talked about what's referred to as bond dipole, the individual bond between those two atoms of those elements, will it be polar, nonpolar, or ionic? And again, sort of the greater the difference, the more polar it is, until that point where typically, not 100% of the time, but when you get above 2, then obviously you've gone to a ionic bond and a transfer of electrons in that particular case. The difference in electronegativity is 1.5 between hydrogen iodine and hydriodic acid, which is HI. It looks like this. We drew it. And the difference here is 1.5, which means the arrow would point towards the iodine. And that means that this bond is polar. And because this is a polar bond and it is the only bond in this particular guy here, this means this entire molecule would also be polar. And if the entire molecule is polar, it means it will have what is known as a dipole moment. And that would be D in this particular case. Dipole moments are represented by these arrows as well. So this arrow right here, when it is drawn, represents a dipole moment. Questions on that particular one there? Okay. We'll talk more about that a little bit later on as well in this chapter. So a couple of review stuff that we talked about in terms of electron configuration and charges. Remember that when we look at the periodic table, everybody in group 1 will form a +1 charge. Everybody in group 2, a +2. For the most part, aluminum there in group 3 will form a +3 charge. And then going backwards, remember on the sort of the periodic table, we kind of go groups 1, 2, 3, +1, +2, +3 for aluminum. We skip 4, and then we kind of go backwards, 5, 6, and 7 for our nonmetals, -3, -2, and -1 in terms of the normal charges that are formed by those guys. As we talked about with our representative elements, the whole purpose of gaining and losing electrons, especially in an ionic compound, is that they do end up with the same electron configuration as the noble gases. Again, that's really the whole purpose of it. Our metals, when you look at the periodic table, metals back up to the noble gas that comes before them. Non-metals basically will go forward to the noble gas that comes after them on the periodic table. And that's a result of them sort of gaining and losing electrons. So as we sort of talked about before, if you took something like sodium, which has 1 valence electron, and you put it together with our chlorine here that has 7 valence electrons, Again, what's going to happen is this is going to transfer. It's at that point when the sodium then loses an electron. The chlorine gains that electron and becomes negative charged at that point. And as we talked about a little bit last time, this is sort of how we represent ionic bonding here in Lewis structures. But what's really happening when we look at the configuration or electron configuration for these guys, this is neon 3s1. This is neon 3s1, 3p5. So what happens is when the sodium loses an electron, it ends up with 10 and ends up with the same configuration as neon. When chlorine gains the electron, it goes right there, and that means, sorry, 3s2. That means that it gains that electron and moves it forward to 18, and it becomes the same electron configuration as argon. Now, they have both achieved noble gas configuration by gaining and losing electrons. And that's really the whole purpose of all bonding, is for everybody to sort of end up exactly like the noble gases in terms of their electrons, as we talked about before. Again, noble gases are extremely stable and very happy just the way they are. And again, that is sort of the goal of both types of bonding, both ionic and covalent bonding. So as you can see here from this table, I think from your book, you can see as they gain and lose, especially our representative elements, as we talked about with electron configuration, they do end up at that noble gas configuration. Different, though, is our, as we talked about, transition metals. They typically don't end up at noble gases, but definitely everybody in the representative groups, which is 1 through 8, are sort of end up that way. So as we talked about as well, and again, some of this should be reviewed from what we were talking about when we did electron configuration in the last chapter, our representative guys will make ions by losing enough electrons to go backwards, and our nonmetals, again, will go forward. Ionic bond creates a neutral compound, so that's something we also talked about before. When we put anything that's a positively charged guy, cation, together with a negatively charged guy, we always want the overall charge to be 0. So for example, if we took calcium, which has a +2 charge, and we took fluoride, which has a -1 charge, and put them together, in order to put those guys together properly, we actually need 2 of these guys to balance out the charge, right? And when we balance out the charge, that ends up giving us CaF2 as the proper formula. Again, when we put the guys together, we have no charge on the formula for the compound, but it is representative of 2 things that do have charges. And the reason that we put them together like this, where we get a charge of 0, in the simplest way to get it to 0 is really because of bonding. And if we look at what's happening here, calcium, which is group 2, has 2 valence electrons, and it has an electron configuration of argon 4s2. And let's say we just put it together with 1 fluorine here, which again, fluorine here has basically 1s2, 2s2, 2p5. Now, what's going to happen in this case is our calcium is going to give up an electron. So this electron heads over to our fluorine, and our fluorine will pick up an electron. A couple of problems happen at this point. This fluorine is now full. It's got 8 electrons by picking that up. It cannot take any more electrons. The problem, though, is with calcium is it still has 1 more electron it needs to get rid of in order to get back to the noble gas configuration of argon. So it's not going to be happy just giving away its 1 electron. And that's really why we actually will need a second fluorine here, because the second fluorine now can pick up the second electron and accept it. And that's really the real purpose why we say we need to balance out the charge here. The purpose of balancing out the charge is to make sure that everybody gets to that noble gas configuration. What we will end up getting when that happens is we will get our calcium that now has a +2 charge, which means it was able to lose both of those electrons and ends up with the same configuration as argon. We will end up with one fluorine that picked up one electron and became negatively charged. We will end up with a second fluorine that picked up one electron and became negatively charged. And what these both then have in terms of their configuration each is they both gained one electron there, which made them both get up to 10 electrons. So both of these F minuses now have achieved neon's configuration. So this is really the reason why when we put ionic compounds together, positives and negatives, that we want to put them together in the simplest way that will give us a overall charge of 0. Because when we do that, that will essentially make sure that everybody in that ionic bond has achieved noble gas configuration. So that again is really why when we put them together, we end up with a couple more, say fluorines in this case, just to make sure that everybody gets to that noble gas configuration. Because without that second fluorine, if you look at the periodic table, calcium, if it could only lose one electron, will pretty much end up at potassium, which is not a noble gas, and it doesn't really do it much good. So it does need to get rid of that extra electron. So in order to take it, because nobody could have more than 8 really in most cases, we need that extra fluorine. Question on that there. Okay. All right, so as we talked about, I think before, again, always positive negatives. We want to put them together in the simplest way that gets us no charge. And again, that really is the basis of that, is gaining and losing electrons so that everybody in that ionic compound has achieved that noble gas configuration. What is the expected ground state electron configuration for Te with a -2? So take a second there and see what you come up with. Te is 52, by the way. Okay, so let's see here. The correct answer is like C, I think. And you could do this relatively sort of quickly. You could just try to find Te there on our periodic table. If you look at Te, like I said, it is right there at number, where did I see it? 52. Right. And if you just look at what's coming up there, we got I next. And then we got our noble gas there of xenon, which is 54. This is period number 5 on the periodic table. This guy is in the P section, so it definitely should end with that. And again, going backwards, it would be 4D10 and 5S2. Remember that at the beginning of period 5, our first 2 is 5S. And then remember that that is 4D. And then coming after that on the periodic table is 5P up to xenon there. So gaining those two will get it to its noble gas configuration. And when we look at what is correct electron configuration for the most stable form of a sulfur ion, Again, we could look at this relatively quickly and figure it out. As we talked about, sulfur is group 2, which means it will get a -2, which should end it at 18 electrons in that particular case, as it started with 16, and the -2 means it ends up with 18. And that 18 would be argon's configuration, so we're looking for the one that is 18, and that should be, looks like perhaps D there in that case. And again, you could also just look at the periodic table and go, that's sulfur, and going down the road, argon would be our noble gas. So it needs to go 1 and 2 places there to get to our noble gas configuration. All right. So as we've talked about, as this is the one I just showed you, which is calcium. Again, as we talked about, you can do sort of the switcheroo. A lot of times people will do that move and go, okay, those are our subscripts on the bottom. And it does work, again, most of the time, but not 100% of the time. So again, good idea just to think about, like we've been talking about, to balance out the charge. So obviously we need an extra fluorine, as we talked about and saw in that last one. So we would have CaF2 as our answer in that particular case. Same thing here with sodium and nitride. We got +1 and -3. So again, we need a grand total of +3 on this side. So that's going to be 1, 2, and 3 sodiums that are needed. So we should end up with Na3. And again, in this case, you would be okay if you just kind of blindly did the switcheroo, but again, does not really work 100% of the time, but 90-ish, 92% of the time. Not too bad, I suppose, to go that way with it. Question on that one there. Okay. Whoops. So aluminum and sulfide. So aluminum is group 3, which means it should have a +3 charge. Sulfide is group 6, which means it should have a -2 charge. Again, the common number here is 6. If we want to kind of put that together, that means to get my aluminum to 6, I need 2 of them. To get my sulfide to 6, I need 3 of them. And again, that will give us Al2 for our 2 aluminums and S3 for our 3 sulfides. Again, +6 and -6 there will give us overall charge of 0. Any questions on that there? Again, that should be a little bit of review. We, I think, covered that in an earlier chapter as well. But again, always ionic compound, metal, non-metal, always want to put them together with no charge in the simplest way to do that. So not the largest way to get no charge, but the smallest way to put them together to get you to a charge of 0. So as we talked about, large amounts of energy are required really to separate ionic compounds that results from a reaction of a metal and a non-metal. The strong bonding in ionic compounds results in attraction between oppositely charged cations and anions, and that attraction is a very strong, what is sometimes referred to as an intramolecular force. And that intramolecular force, which is ionic bonding, is a very, very strong attraction. And again, that is sometimes referred to as an electrostatic attraction that occurs. And again, as we just talked about earlier, the bigger those charges, the really stronger they come together. The less the charges, positive, negative, they still come together relatively strong, but not as strong as well. So when they do get together in sort of an ionic compound, when we have a metal and a non-metal, they do really try to arrange themselves in a way in which all the positive charges and negative charges, try to get away from each other as best they can. But they, all the positive and negative charges come together, but they try to get the positive and positive charges away from each other as best they can, and the negative and negative guys sort of away from each other as best they can. One of the really nice things about sort of ionic compounds is when they do come together in the solid state in a sort of 3-dimensional structure, they come together in a very organized pattern and a very repeatable pattern. And you'll learn about this in like probably 1A perhaps, but you literally could just take a piece of this structure here, which is sometimes referred to as a unit cell. And that little piece of that three-dimensional structure is so repeatable that you could just basically keep putting that same piece together and you could rebuild the entire sort of three-dimensional structure. There's that much sort of repeatability and long-range order that happens when ions come together that you literally can just take almost just a small snapshot of how they come together, and just from that little sort of square of it, be able to recreate sort of the three-dimensional structure that occurs. So cations are, as we also, I think, talked about with our electron configuration and stuff like that, always smaller than the neutral guy that they came from. Again, the idea there is in order for them to become positively charged, they have to lose electrons. When they lose electrons, their electron cloud gets smaller. The overall size of the ion is smaller. While anions are different, when they gain electrons, their electron cloud gets larger because they have more electrons, and thus they always look sort of larger than their originals. And that's why when people sort of draw ions, the positive guy is always usually drawn smaller than the negative guy, again, because he's sort of lost electrons in his overall cloud, he's gained electrons, and it's at that point now that there's a very strong attraction that's going to happen between the two ions. They're going to come together. Again, you got that bigger negative charge, and it's going to grab that positive guy and attract them. Again, no sharing of electrons here. That complete transfer of electrons that basically occurs. And as you can see here, a reminder that when we have these metals and nonmetals by themselves, they don't have charges. So it's only when a metal and a nonmetal come together that a charge does form. So sometimes people think if I just have like, you know, calcium by itself, it has a +2 charge always, and it doesn't. So if you have a piece of calcium metal, it does not have a charge. Again, things will only really gain charges when those two guys come together and you have that transfer of electrons occurring. And that's when we get those charges. That's when we get those attractions. If you have chlorine gas by itself, no charge. You have calcium metal by itself, no charge. Iron metal, no charge. But if you take the calcium and the chlorine and put them together, you get calcium chloride, where they both have a charge at that point. So again, it's really only when they start combining that we do see those charges occur. And again, here's sodium chloride. This is what solid sodium chloride looks like. And again, when you go to dissolve something like solid sodium chloride, what essentially happens is like a water molecule comes in and pretty much plucks off an ion, and another water molecule comes in, plucks off an ion. And what ends up making something like that dissolve is it eventually, each of those ions gets surrounded by water molecules. So the water does two things. It makes it look like the sodium chloride disappeared because you can't see it anymore, but all those ions just get trapped in all the water. And it also keeps these two ions from getting back together. And that's why the solid will sort of disappear or dissolve. And it's because it's basically all those ions get trapped in the water. And that's also why it will come back together, right? If we heated up something like sodium chloride and we dissolved off the water, without the water, they will come back together and that solid will reform. And we will see, like, you know, a white solid that's left over.
Sodium chloride is typical of ionic solids. The crystal contains alternating sodium cations and chloride anions packed in a three-dimensional array. Ionic solids are brittle if deformed and will fracture along planes of packed ions.
That was exciting. Even I was surprised by that. All right, that's a good deal. All right, so polyatomic ions work basically in the same way. Polyatomic ions, as we'll talk about, are basically groups of nonmetals that are held together by covalently bonded guys. So polyatomic ions, which is something like nitrate, which is right here. So nitrate, which is an ion, and that's a polyatomic ion. It's an ion because overall, when you sort of draw the Lewis structure for something like nitrate, looks something like this. It actually is a covalently bonded guy because these are all nonmetals. Nitrogens, oxygens are all nonmetals. So they're going to share the electrons. But the overall charge that occurs when all these guys get together is it does overall have a -1 charge when it does come together. So polyatomic ions are sort of weird sort of things for a lot of people to understand. They technically are ions because overall they do have a charge. And by the way, that one nitrogen, those three oxygens will always stay together. They'll never break apart into separate nitrogens and oxygens. They move around as a whole unit because they are covalently bonded together. So because they are covalently bonded together, they tend to move around as one whole unit with the overall unit having a -1 charge. But they do sort of behave as ions because overall they do have a charge. So when something like sodium gets next to it, which is like sodium nitrate, what we see here, there is actually no sharing of electrons between these two guys, the sodium and the nitrate. They are held together by the positive negative attraction between the two ions. But if you look at just the nitrate by itself, there is sharing of electrons between the nitrogen and the oxygen. So it's kind of an unusual sort of things, polyatomic ions, but they're basically groups of nonmetals that are technically covalently bonded together, but still have an overall charge. So when the whole unit interacts with another ion like sodium, they come together as well in this sort of three-dimensional lattice type of condition. All right, so again, these are some formulas here when we predict them. These are some polyatomic ions.
To work out the formula of an ionic compound, we first select a cation and an anion. Some possible cations are shown here in blue.
All right, we talked about that. That's good. All right. So here we have lithium and sulfate when it comes together. So same idea when we put these guys together. The sulfate, the entire thing here has a -2 charge. And we're really putting it together with lithium that has a +1 charge. So in this particular case, we need more lithiums. So we need 2 lithiums. That gives us a +2 charge that balances out the overall -2 charge for our polyatomic ion. And the correct formula should be Li2SO4 in this particular case when it comes together. So you want to think about those polyatomic ions as really just ions. They just happen to be groups of nonmetals together. And we do put them together in the same fashion as we put other ones together. Now, as it mentions here, there is a case where you could get or need more than one polyatomic ion when you put it together. And in that case, you do want to make sure that you put parentheses around the polyatomic ion. In this case, we don't need it because there's only one sulfate. So for example, if we look at this, if we put barium and phosphate together, again, the phosphate here is PO4. It has a -3 charge overall. Again, that one phosphorus and 4 oxygens will not break apart or move apart. They all stay together. So we're basically putting something with a +2 charge together with something with a -3 charge. In this case, same idea. Our common number there is 6 to get us to 0. That means that we need 3 of our bariums, and we would also need 2 of our phosphates here. And again, 3 bariums gives us a +6 overall. 2 of our phosphates gives us a -6 overall. So when we put the formula together, we do Ba3, PO4. And in this case, if you go, I just need 2 of those and put a 2 there, that would not be the right formula like that, because basically that would indicate that you have 3 bariums, 1 phosphorus, and 42 oxygens, which is, I don't think, what you're trying to do. We actually only want 8 oxygens. So whenever you have more than one polyatomic ion, you do need to put parentheses around it. with the number on the bottom there to indicate how many of those polyatomic ions you have. So with those parentheses, it says we have 2 of these PO43 units. And with the 3 there, we have 3 of the baryons with a +2 unit. So you always want to make sure that you do put those parentheses around a polyatomic ion when you have more than one present, again, to help indicate properly the number of those units that you have there without messing it up. Question on that there. And that goes for either a most polyatomic ions, as we'll see when we officially get into nomenclature. Most polyatomic ions pretty much are negative. There are pretty much a couple that are positive, and one positive guy is ammonium, which we'll see here on the next page. And if we were going to put these guys together, again, same approach. This is carbonate. The overall guy has a -2 charge. And this is ammonium here. That 1 nitrogen, 4 oxygen stay together. Again, we're basically putting a +1 and a -2 together. What that means is we do need more of the ammonium here. So we will put both of those guys together. And we need to also, again, put parentheses around it with the 2 on the bottom. And since we only have 1 carbonate, we don't need parentheses around that guy. So it should look something like this here. Any questions on putting our formulas together, especially ones that basically contain polyatomic ions? And just so we're clear, what we're really seeing here in terms of bonding, to get it back to sort of bonding, is if we drew NH4 plus correctly, again, it would be sharing of electrons, covalently bonded guys between the nitrogen and the hydrogen. And again, this overall guy has a +1 charge. And if we were to draw carbonate, it would look something like this. And again, this would have a -2 charge. So again, the carbonate here, carbon oxygen, sharing electrons, covalent bonds in here, covalent bonds in here. But overall, they both have a charge, or they're ions. So they will come together. And basically what we're saying is we need not one of these structures, but we need another one of those guys floating around as well to help us out balance the charge, basically. So our 2 positive ions coming together with our 1 negatively charged -2 ion. Again, no sharing of electrons between all the ions, but if you take each of these polyatomic ions individually, they are actually held together by covalent bonds and sharing of electrons. Question on that there? All right, so let's take a look at some other stuff here. Structures of ionic compounds are usually described as packing of anions with smaller cations fitting into the interstices. So smaller guys are going to be cations, right? And larger guys will be anions. So it looks like A would be the right answer here. Again, packing of our anions, which are negative, with our smaller cations, which are positive. Again, the attraction of the positive negative going to hold that guy together. Correct formula when we do magnesium and chloride, magnesium being +2, chloride being -1. So again, when we put this together, we need more of this guy here. We need a grand total of 2. That again is going to allow this guy to properly get to noble gas configuration. So it should be MgCl2. Again, bonding wise, what's happening? Magnesium with its 2 valence electrons and its neon 3s2. And our chlorine here with its 7 valence electrons at 1s2, 2s2, 2p6, 3s2, and 3p5. Again, when the magnesium gives away the electron, that's going to fill up this 1 chlorine, but not going to do magnesium good because he needs to lose those 2 electrons. So again, in this case, we need a secondary chlorine here to pick up the 2nd electron there. And at that point, all 3 of those guys, the magnesium ends up with a +2 charge and neon's configuration. Each of the chlorine will pick up an electron and become negatively charged and basically end up with argon's configuration on both of them. Question on that there? All right, so in terms of silver, silver is one of those guys that has a fixed charge. Silver is +1. Sulfide is group 6, which is -2. Again, putting this together tells us that we definitely need more silver. Going to give us 2 silvers to balance out the charge and 1 sulfur. So it looks like perhaps B there would be our right answer in this particular case. Any questions on ionic bonding, putting our formulas together, what's happening in terms of the bonding? And again, the purpose of that ionic bonding, as we talked about, is really to make sure everybody hits that noble gas configuration. All right, so let's talk about covalent bonding and sort of, again, the sharing of electrons and maybe a way to sort of represent these with Lewis structures. So a molecule that is composed of atoms that are bonds together through sharing of electrons through their atomic orbitals basically is covalent bonds. And as we talked about, I think a little bit last time, the purpose of covalent bonding is also to make sure that everybody really achieves that noble gas configuration. The difference here with covalent bonding is we're typically dealing with 2 nonmetals, and they're going to share those electrons. And again, as we talked about earlier, they may share those electrons equally, they may share them unequally, but there's some aspect of sharing that's happening. And when we look at electrons, for example, like when we get our 2 fluorines together, since they obviously have the exact same electronegativity, when they come together, they are going to choose to share those electrons, which again, you could represent as dots. Where the electrons in the middle count for the fluorine on the left, and if you count them, that is 8 electrons. And the fluorine on the right also gets those guys in the middle there, which count for 8 electrons. And again, those guys on the periodic table with 8 valence electrons are our noble gases. So by sharing electrons here, they're able to basically reach that noble gas configuration. We could also show that by using a line here between the 2. And one line represents 2 electrons or a pair of electrons. And when we look at certain electrons in these pictures, as I think we might have covered earlier as well, all these dots which have no element on the other side of them. These are all what are referred to as lone pairs, are non-bonding electrons. And much like the name implies, they are not involved in any bond formation. And that's different than the line that's here, are these 2 dots right here. These are what are known as bonding electrons. And much like the name implies, those are electrons that are involved in bond formation. So when we draw sort of Lewis structures, definitely for covalent compounds, we always want to show all those electrons, both the non-bonding electrons are the lone pairs and also the bonding electrons. And it's really your choice in terms of the bonding electrons, how you want to show it. If you want to use lines, perfectly good. I personally will use lines. If you want to use dots to represent the bonding electrons, you could do that as well. Either way is fine, but you should always show, obviously, the bonding electrons because they're bonds, but you also obviously should always show the non-bonding electrons or the dots as well. And that's the part that a lot of times people will kind of leave off their pictures is, all the non-bonding electrons. Really important to show in the Lewis structure because also later on, it will help us determine the geometry of these guys by looking at how many non-bonding electrons are there and bonding electrons are present. So the description of valence electrons is our Lewis structure. And we could do that by drawing Lewis structures, which we'll talk about how to do that in just a second. We could also predict geometry, which is known as VSEPR, which stands for valence shell electron pair repulsion model. And we could describe them in terms of the orbitals that are sharing electrons that have our lone pairs in them. So let's talk about Lewis structures. When we draw Lewis structures, it does show really only the valence electrons. So only the valence electrons are shown when we're dealing with Lewis structures. It's important to remember that obviously there are other electrons in each of these guys, but just the valence electrons are shown. Again, the valence electrons equals the group number. So everybody has the same number of valence electrons as whichever group on the periodic table they are in. And a couple important sort of rules there. Everybody needs to achieve the noble gas configuration, which is sometimes referred to as the octet rule, which means pretty much everybody will continue to make bonds until they have 8 valence electrons. That is the octet rule. The one exception usually is the duet rule. And a duet rule means 2 valence electrons, and that is our friend hydrogen. Because again, if you look at the periodic table for hydrogen, hydrogen is number 1, followed by number 2 on the periodic table, which is helium, and that is a noble gas. So hydrogen only needs to get to helium to be happy. So hydrogen should only have 2 electrons total, which means when you draw hydrogen, it should always be on the outside. It should look something like this. 1 line and a hydrogen, or if you're going to do dots instead of the line, like that. But you should never have hydrogen that has dots all the way around it because that is definitely wrong. Never double bond a hydrogen, never triple bond a hydrogen, and put dots, definitely double wrong. So hydrogen should always look like this, no matter what the situation is. And it can never find itself in the center because if it's in the center, it's going to have more than 2 electrons. So it'll never be in the center either. So here we have our 2 ions here. And again, when we take a potassium and a bromine together, potassium started with 1 valence electron, and bromine, which is group 7, has our 7 valence electrons. And again, our potassium is going to transfer that electron over. When it does, it becomes K+, and K+ ends up with argon's electron configuration. When the bromine gains that 1 electron, it becomes the bromide ion, and it goes forward from 35 to 36 and ends up with ends up with krypton's electron configuration. And again, this is an ionic compound, metal, non-metal, no sharing of electrons here. And that is why when we draw these Lewis structures for ions, it is always important to put the charge. So you always want to make sure the charges are included if you're drawing something that's an ionic compound. And usually, a lot of times around the negative guy, they'll also put brackets, and that's usually very common. And again, that just helps people understand that when they see this drawing with the charges, there's no sharing of electrons. This is an ionic bond, and we've had a complete transfer of electrons from our metal to our non-metal. Any questions on that there? All right. So let's talk a little bit about drawing Lewis structures or writing Lewis structures for some covalent guys. As I just sort of drew earlier, when we take our 2 fluorines, especially when we have our 2 nonmetals coming together, they're going to share electrons. And again, those electrons that are being shared between the 2 atoms are what are referred to as our bonding electrons, as we just talked about. And they do count for each of the fluorines. And again, at that point, when they share those electrons, both of those fluorines hit the magical octet rule there with 8 valence electrons. And that makes them really happy, again, because they have now pretty much become very much like the noble gases in a very stable sort of way of doing that. All right. So there, in addition to the duet rule, which is basically hydrogen needs 2 electrons, and the octet rule, which for the most part everybody else needs 8. There are some exceptions we'll talk about to the octet rule. So let's just talk about some of these rules again. The duet rule, as I mentioned, really is for hydrogen. It just needs to get to that helium configuration. And again, in the case of 2 hydrogens coming together, these 2 electrons, which are going to be shared, 1 electron from each, gives this hydrogen on the left 2 electrons, this hydrogen on the right 2 electrons, again, allowing hydrogen to hit that helium configuration in both cases and being very stable. Again, you could show it like that. You could show it with just a line. Again, the line representing our 2 dots there. So again, you could do it either way, both having there. And again, that's the duet rule. Now, there is some exceptions to the octet rule where everybody needs 8 to get there. And one major exception is what is sometimes also referred to as a incomplete octet. And in an incomplete octet, what it basically means is there are certain elements that are perfectly good with less than 8 electrons. And the prime example is right here. This is our guy boron. He is perfectly fine and okay with less than 8 electrons. And that's the one you'll come across the most, I think, probably in terms of an incomplete octet, is that boron. Technically speaking, aluminum, which is right underneath boron there as well, can do it. Beryllium as well, but typically beryllium and aluminum are considered metals. So they more will be in like ionic compounds, but sometimes you'll see those sort of elements plop into that sort of exception. But probably 9 times out of 10, or even 9.9 times out of 10, if you're doing sort of an incomplete octet, boron is going to probably be the element that will be involved with it. So sometimes called the sextet rule. Again, it has only 6 electrons around it, 2 for this line, 4 and 6 electrons. Again, 2 for each of the lines that are there. So 2, 4, 6 electrons around the boron there in the middle. And then what most people, and that's what it looks like in sort of a space field sort of model, the hydrogens being kind of the green guy and the blob in the middle there being our boron. These are also sometimes what are referred to as being electron deficient, obviously, because they have less electrons, and makes them really want to a lot of times bond and kind of pick up some electrons because of that kind of deficiency in the number of electrons. But most of the time, everybody is really aiming for that octet rule, which pretty much means that everybody will continue to make bonds until they have 8 valence electrons. And in certain cases, that may require a single bond like we see here, may require double bond or triple bond, as we'll talk about here in just a second, to get everybody to those 8 electrons. So sometimes if you just kind of single bond everybody, it doesn't allow everybody to get to those 8 electrons. So sometimes it's needed to make some extra bonds, and things will continue to kind of make those extra bonds until they get 8 valence electrons around it. So here, in the case of F2, as we've seen before, by sharing those electrons, each of the fluorines here does end up with those 8 valence electrons. So it's perfectly good in this case. As we'll also see a little bit later on this chapter, there's also an exception to the octet rule, which is sometimes referred to as an expanded octet. And as we'll see, I think a little bit later on this chapter, there are some guys that can go more than 8. And we'll talk about which ones can do that a little bit later on. But most things will maintain those 8 electrons. And pretty much in this class, most things will basically obtain the octet rule, or basically obey the octet rule. When you take 1A, everybody will go over 8 a lot. So that's a very common sort of exception that we'll talk a little bit about here but you'll definitely see a lot more of it if you take 1A in terms of that expanded octet. So like I mentioned before, sometimes to get everybody there to a 8 electrons, a single bond is all that's needed, and a single covalent bond, because it's covalent, we're sharing electrons here, and we're sharing a pair of electrons. So again, a single bond represented by one line represents 2 electrons, or a pair of electrons. So here again, this single line here is a pair of electrons that are being shared by, again, both of the hydrogens, allowing each of them, again, to get to your 8 electrons each. As I think we might have talked about a little bit earlier as well, sometimes that is not going to happen with single bonds, and sometimes you do need double bonds. And this is carbon dioxide, and carbon dioxide actually needs to make a double bond on both sides here to do that. And by doing so, if we kind of circle this oxygen here, it has 2, 4, 6, and 8 electrons by that double bond. Oxygen on the left-hand side, same deal, 2, 4, 6, 8 electrons. And then our carbon, by making those 2 double bonds in this particular case, ends up with 2, 4, 6, and 8 electrons as well. So all 3 of those guys ends up with 8 valence electrons, and they've all now, by making those double bonds in that particular case, are able to achieve that noble gas configuration and be extremely happy in that configuration. And I think we might have saw this example the other day. Nitrogen, in order for nitrogen with the 2 nitrogens there, in order for it to reach that noble gas configuration, it actually needs to do a triple bond. So just so we're clear as well, let me go back. Maybe. A double bond, just so we're clear, is 2 lines, represents 4 total electrons, or 2 electron pairs, is what happens with our double bond. So again, each line representing a pair of electrons, 2 lines represents 4 total electrons, or 2 pairs of electrons that are being shared, while our triple bond means 3 lines represents a total of 6 electrons, or 3 electron pairs being shared. And again, in this case, nitrogen on the left is going to be sharing 1 pair, so that's 2, 4, 6, and 8 electrons. Nitrogen on the right, by sharing that triple bond, 2, 4, 6, 8 electrons. Again, both of these guys hit those 8 electrons. If you just laid up a single bond like this for nitrogen, which I think we might have drew this the other day, and if you just kind of went through and you distributed all your electrons, that is 10 electrons. That's the total number of electrons you should have. And with a single bond, you can see that the guy here on the left is very much short, only has 4 electrons. So we need to bring some electrons in to make a double bond. We need to bring some electrons in to make a triple bond. And we do end up with this guy here where they all get 8. No, so we're going to talk about actually right now, I think, hopefully, with these slides, hopefully we'll get to actually how to draw Lewis structures. We're going to talk about the way you actually draw Lewis structures, and the way that you should sort of apply electrons is actually when you're drawing Lewis structures of 2 atoms or 2 or more atoms coming together, you should always place those electrons on as pairs, basically. And that's the way you should always do it, and you'll usually get the right sort of structure. If you're just sort of have just the one sort of atom by itself, it's not really bonding with anything, you can't put one at a side and then pair them up. But typically when we draw Lewis structures, where we're putting 2 or more atoms together, we do apply the electrons as pairs and stuff like that. And we're going to talk about those rules right now. So let's talk about really the rules to drawing Lewis structures. And a couple of important things here is... yeah, I don't really care what it says. All right, so let's just talk about the right way to draw it here. All right, so basically the first thing that you want to do is you want to come up with really the logical arrangement for the atoms. So what that means is sort of the logical way that all those atoms really should come together when we're drawing Lewis structures for covalent guys. A couple of things that will help you decide how the structure should be is typically in the center is the least electronegative atom. So usually the center atom is the guy that is the least electronegative. Usually you will never find hydrogen or fluorine in the middle or in the center. And again, that is because fluorine is the most electronegative and hydrogen can only have two electrons. So again, if you put hydrogen in the middle, not going to work right. So usually least electronegative in the middle. Hydrogen, fluorine should always be on the outside, never in the middle. Next, what you want to do is count up the total number of valence electrons. And that means that if something has a charge, something has a positive charge, like an ion or a polyatomic ion, we need to subtract from the total, because that is why it became positively charged, because it lost electrons. Something has a negative charge, you need to add electrons to the total. Again, if you don't take into account the charge on a polyatomic ion you're trying to draw, you will end up with the wrong structure because you'll have not enough electrons, too many electrons, something like that. Now, why this guy is really important is when you figure out the total number of valence electrons, your picture has to have exactly that number of electrons in it to the nose. Can't have any more, can't have any less. Got to hit that number right on the bat. Once you do that, what you want to do is make a single bond from the center atom to each of the outside atoms. So a single bond is basically one line, right? And one line represents two electrons, as we've just been talking about. So what you're going to do is after you figure out how many single bonds you've made, you're going to figure out how many electrons you have left. And all the electrons that you have left from your total, from number 2, you're going to put on the outside atoms as pairs of electrons. So those are dots. So you're going to go on the outside atoms, put dots all the way around all those outside atoms until everybody's got the magic octet rule there, right? Everybody's got 8 electrons, except for hydrogen, which obviously does not get dots because it just needs 2. And once you've done that, you should have distributed all your electrons on the outside atoms. If you still have electrons after you fill up all the outside atoms, then you should go to the center and put on as dots. If you still have some left over after you fill up all the outside ones, go to the center atom and put them on as dots. The last thing that you want to do is you want to make sure that once you've distributed all your electrons, that everybody meets the octet rule. It's at that point, if somebody does not meet the octet rule, if there's an atom that does not meet the octet rule, you want to try to fix it by making a double bond or a triple bond. So that's a really important sort of organization in terms of how to do it. You want to go single bond everybody first, get all your electrons distributed properly outside first in pairs, and then inside center atom, and then make sure everybody has 8 electrons. If they don't, then you want to fix it by making a double bond or a triple bond. You typically do not want a double bond or triple bond out of the box, which is what everybody wants to do when they draw these pictures. They just want to like start double bonding and triple bonding things. Is not a good idea to do that. You should wait and only double bond or triple bond to sort of fix something that is not correct. Question on those steps. So just to kind of show you an example that we'll go through one here, and we're going to ignore what's on these slides because it's giving me a headache. All right, so we got NF3 here. Let's do this example here. So NF3, if we were going to draw NF3, what we would want to do first off is we want to count up the total number of electrons, valence electrons. So nitrogen is group 5, which means there's 5 valence electrons for nitrogen. There's 3 fluorines, which means each fluorine is group 7. So that's 21 and 5 is 26 valence electrons. So this number is really important because when I am done with my picture, I need to hit that number exactly on the nose. So arrangement of this, logic tells us that if we have 1 element and 3 of something else, the 1 should be in the middle. But we will put the nitrogen in the middle. The fluorine will go around on the outsides. Nitrogen will go in the middle because if you look on the periodic table, nitrogen is less electronegative than fluorine. So nitrogen should be in the center. By the way, I could put the fluorine up on top instead of on the bottom. It doesn't matter. So you could have arranged it if you wanted to this way as well. It doesn't really matter. So what I'm going to do at this point is now that I have my logical arrangement with my least electronegative in the center, I'm going to do 1 single bond to everybody. And by doing 1 single bond to everybody, I have now put 2, 4, and 6 electrons in my picture. If I subtract 6 off of my total, I am left with 20 electrons still to go. Those 20 electrons go on the outside ones in pairs. So I'm going to go 2, 4, 6. That's going to fill up this fluorine. 8, 10, 12. That's going to fill up this fluorine. 14, 16, and 18. That's going to fill up this fluorine. I have now placed 18 electrons on my picture. I still have 2 more to go, and everything on the outside is filled up. So now that I filled up everybody on the outside, now I'm going to go to the center. And on the center atom, I'm going to put it on as a pair of electrons as dots. That is now 20 total electrons have been applied to my NF3. And what we want to do at the end is figure out, is this has 8 electrons. So we look at the nitrogen, we got 2, 4, 6, 8. I'm sorry, the fluorine, 2, 4, 6, 8. Each of the fluorines are exactly the same, 2, 4, 6, 8, 2, 4, 6, 8. And our nitrogen in the middle, 2, 4, 6, 8. Everybody has 8 valence electrons. We have a grand total of 20 electrons. This would be the correct Lewis structure here for NF3. Question on that there, on that steps. Okay, we will stop here for lecture. We will go off to the lab in about 15 minutes, and we're going to probably continue talking a little bit more about this since that's what the study assignment's about. So we'll do some more examples, how to properly draw these things, and probably continue lecturing, I think, and stuff like that. All right, any questions on any of that? Make sure you put here in the chat, and I'll see everybody in about 15 minutes.